Welcome everyone to our special 2 p.m. seminar. Thank you for staying after the last meeting. So it's a great pleasure to introduce Huey-Wen Lin, who's visiting us en route to the confinement conference in Cairns that is happening. Is it this week or is it next week? Next week. Okay. So yeah, it's very lucky that you're able to have a stopover in Sydney. Huey-Wen is coming from Michigan State University. He's an expert on lattice QCD, which is a topic I think we all need to know a little bit more about. It's very important, and it's none of us know enough about, I think. So it's great that you can come and introduce us to this, and I'll leave it in your hands. So thank you very much.
Thank you. And thank you for having me. And it's very nice to visit. I walked around the university this morning. Okay, so popping the heart on the matter. So this is something that we all actually learn how to do that when we are very little. So it's going to be a topic that's too foreign for anyone, right? And then as you grow older, obviously you smash things with more style, and some people can want to realize for it, right? And so you are very handy. You can be experimentalist. You can work in this big collaboration and making discovery. And I'm being actually not so great as I tried to be experimentalist when I was in my early years. I wasn't really great at that. So they were just something that meant for everyone, right? And so I started to explore other career paths with my PhD study. And then I run into this area that I can actually do some interesting calculation using supercomputers. And so one of the things I want to point out with the supercomputer is sort of this is kind of a really growing area. And so we are limited by the availability of the supercomputer because we do a lot of these high performance calculations. And so the supercomputer is like skyscrapers, basically, right? You have this top #1 building at once, and then very soon another country build another taller building, and then you are not there anymore. Same thing with the supercomputer. So for example, the Fugaku is one of the Japanese supercomputers that was #1 in June 2020. And very soon, about November 2021, got knocked over by someone else built a bigger computer. So today, actually, I had to look it up today, just right before the seminar to see what's the current #1 right now. So the #1 right now is something called Frontier supercomputer in US. It's hosted at one of the national lab in Tennessee. And so this great sort of competition actually also help really benefit people like me who are using supercomputer to do the research. We are able to do more than what we can many years ago. So I'm going to talk a little bit about that. So I'm going to briefly sort of introduce a bit about the standard models and then how we do such a calculation using supercomputer. And I'm going to give you brief examples. And I hope I can finish this in about 45 minutes. Right. So many of you have probably seen this mug in the certain gift shop or somebody else who having one in the group. So, the standard model is, simple-ish, but it's also very complicated as we are still trying to really reveal a lot of mystery from that. And the QCDs, the zoo, particle zoo. So the QCD really just have a small sector. So we are trying to focus really mainly on the interaction between the quarks and gluons and then things in between. And most of the time we study with the lighter quark family rather than heavier one as they decay really quickly. And so the QCD really there's strong interaction of the quark and gluons, and then there's a gauge theory sort of link all this together in a way. And so if you are not familiar with the QCD, let me see, I can get this to work. Okay, sorry, yeah. So, all right, so this is, sorry, the audio is not working, but it's something that you can learn, or you are doing something related to QCD, like your family and your friend who are not familiar with this. So there's a game that you can download on the phones, either from an Android phone or an Apple phone. So it's a very simple game, something that's kind of inspired by my own children who are like wondering, asking what I'm doing. In a way, it's always very hard to describe to somebody like, the particle you can see. We can even see those particles in the lab. So how do you describe to them, right? So this game is a part of my one of my award with the outreach component to try to introduce to people, general public, about what QCD is, because you generally don't learn about that. In US, this is the second year grade school. You have to learn about quantum mechanics, you have to learn about field theory, and by the time there's only a few students left still taking the field theory then, and there's really nobody learned much about QCD. But if you remember roughly what the tire looks like, it's actually very similar. A lot of QCD are simple-ish, right? You form particles, you have this very simple rule, just like a lot of reason that we get into physics, because we like the rule, the symmetry, the simplified things, so that there's a patterns. And so this game is sort of designed to do that, right? So this is actually with the help developed by an undergrad who is not a physics student, he's just a computational scientist undergrad, that's an intern, and we work with him to develop this game. And we have been trying to do this around. So this is a picture of my PhD advisor, and my kids is teaching him how to play the game, which I always thought that's funny, right? And then we do a couple of outreach with the game as well. So I'm gonna skip ahead, right? So the QCD is really describing the color force, right? So we know the QCD is it's very different from a lot of other theory that we learned. Let's say QED, for example, the coupling constant itself, it's a scale-dependent quantity. So at a large energy that we know we can have very nice, what feels like is to, it's expanding anything in very different parameters. So perturbation theory like to expand things in terms of strong coupling constant, which work very well with the QED, and we've done that many, many times. And at large energy, we can do that, so that's great. But as more researchers have been kind of carried along in the high energy regions, right? So a lot of less known area in the lower energy, which in this case is roughly where about a few GeV mid-level, that way the strong coupling get much, much larger. And that's where the perturbation theory tend to be not working as well. And there are a lot of phenomena that's kind of in that areas remain to be studied and understand. And so here I give a few examples why we want to study that low energy, high strong coupling region physics, right? So at a very small scale, for atomic meter scale, 10 to minus 5, we can study the structure of the proton, which is the fundamental building blocks of every visible matters. Right, so there are a lot of questions people still try to understand where the mass come from. It's not just its quark itself, right? The interaction actually contribute a lot of the mass itself. We like to understand more about the protons. So there are some people that really try to launch a program, try to image them as much detail as we can. There are also things like photon distribution function, which I'll talk a little bit more later in this talk. So that can have itself can be useful for new physics search to set up the standard model backgrounds. And we also using a lot for various different cross-section in different type of experiment as well. QCD can also help us understanding why we exist in some levels. So the residual of the proton neutron, they also have this strong interaction of binding the nuclei together, right? So, and how much of that excess energy that that can form stable carbon-12, and then we actually have people. I personally did not do the calculation, but some people in my field actually try to tune this. We do the simulation. We can tune the masses of the quarks, the couplings, right? Then you can actually find too that there's only this area that you can have very stable carbon formed in the universe. Any other set of parameter you won't see that. Right, and the large, actually I forgot I have a mouse here, and then at the astrophysical levels, so there are also things like object like neutron star that was still quite not understood yet, as people have been finding larger and larger radius for the neutron star as they previously did not anticipate it. Right, so it goes to the center of the neutrons. We know neutron star have like tons of neutrons. That's the name. But inside the center of the neutron star may not be only neutron only. That can have other particle that can decay very fast. Something called hyperon, which is a strange quark replacement to one of the up quark or down quark in protons. And there they can have very different kind of interaction that can have different interaction inside that can make the radius large. But we don't really have stable hyperron property that we can study in the real world. So it might be something like we don't have enough information to really fit into some of this study. And there's something like if we can find out more about them, we would understand more of those equational state, and then maybe we can understand more on things like this, right? So, but when you learn physics, you always like to start with, what's the simplest state, right? So in classical physics, the simplest state would be, you would think the vacuum itself, right? It would be the simplest. And it is sort of kind of true, right? Because the vacuum is literally nothing in classical physics. But if you are looking at QCD, it's actually not so simple, right? So this is a QCD vacuum. We use with something called topological charge, which representing the dynamic change of the field and the cell, right? So we know the quark pairs kind of pop in and out multiple times in the vacuum. So by itself is a dynamic configuration. It's not something you can just start in somewhere and then you start with the calculations, right? So that's where. So to overcome and to try to kind of study the strong interaction. So Wilson come up with this idea. It's about late 70s. So he was actually not trying to solve a different problem at the time by introduce something called lattice gauge field. So basically you have the same four-dimensional space-time where I cannot draw them, so I only draw three-dimensional here. And then you basically introduce something called lattice spacing, A here, which is the smallest scale you have, which is corresponding to the highest energy in the system. And then we will put quarks. Quark can only live on specific grid, and then we can try to integrate out the gluon degree of freedom. That because it's field theory, we're tending to turn it into a field. And then they will be, because we were hoping to solve such a problem on the computer, so we cannot literally put infinity space-time on the computer, so we had to truncate them, right? And the truncation of that system will be depends on what you study. Your box should be bigger than the particle you want to study, what sort of property you want to study. So sometimes we know that by guessing, sometimes we know that by looking at the literature. So you want the box to be big enough so your simulation is not changing by that particular parameter introduced, right? So at the end of the day, if the quark mass we put on the system is not physical pair mass, we might be doing a few quark mass simulation and we do extrapolation. And similarly, we can never study lattice spacing at zero. So we always have to start, we'll study multiple lattice spacing and so on. And similarly, multiple values, so we can do that extrapolation. And only when we do all this, that we can reconstruct whatever we calculate and link that to the world we live in, right? So it has been a while, and a lot of people have been like, why you guys haven't solved QCD yet? So one of the hopefully obvious issue is really the computational resources, right? So imagine the state of the art around when the lattice gauge theory was introduced. This is the state of the art computer you can play, which take out something called disk star. I'm not sure some of the students heard of that before, but huge disk star that really take out most of the disk space, right? And then you only have arrow key to do some function as a state of the art game. To today, you can have very small PSP device on your hand and have really amazing vector graphic and all that computational power, right? So it is something that has been progressed quite a lot since the theory was introduced. And in addition, more and more people in my field also work with collaborating with applied mathematicians, computer scientists. So they come up with interesting idea algorithm, and sometimes they dig out like algorithm that was discovered few hundred years ago by a mathematician, but there's no application to that. And they will be able to sort of like, nobody's going to know, like you're going to have so many floating power that like the GPU, for example, right? You have way more floating power than you can use. It can actually use the machine very differently than back in the time when they were discovered. So as a result that we are able to, one of the biggest issues is be able to put that quark mass as close to the physical quark mass as possible. And that's something that we can do. And we also do that in generating the QCD vacuum. So that was roughly another speed up of 10-ish. So that calculation had about 10 years. But I'm just waiting for computer to catch up. Now we can do it in 1 year. And that's big differences in terms of what we can do today. So then how do you do a latest QCD calculation, right? So one first thing would be you need to get some piece of hardware, so some sort of supercomputer or cluster. They come with various different sizes. In US, we have a lot of latest people get together. We try to get money from the one of the funding agency called DOE, Department of Energy. And so we have there's a special call for scientific discovery to accelerating. Oh, sorry, I probably forgot the name. It's one of the call called SciDex for I don't remember the name exactly. Acceleration computing, something like that, right? So we are able to buy some sort of what we call mid-sized cluster that only put for latest QCD people only. So it's small community for small size of machine, but we can do a lot of tests on those machines. And we can set the machine up in such a way that's benefit in our calculation, which we need most of the time, a lot of memory than many other fields. And they are also like different funding agency. There's a National Science Foundation. They like to put different kind of machine in various different universities. So they try to support university computer centers. And so this is one of the machine in Texas. One of the things I really like about them is all their computer there have a theme of the Rangers. So the machine is Stampy. They have 1 and 2, and the storage is range. It's fun. Always find it very funny. And then there are machines also in other DOE lab as well. They have very different calls. And so this one is from Berkeley National Lab, and I like to name the machine after the scientist, and they tend to vary older in general. And so this is one of the machines I use quite a bit as well. And then, if you are young and energetic, when I was doing my PhD, I was doing the calculation that only I was the only one in the group that's doing the calculation, nobody else was. And then so all the machine in our group is being occupied by the bigger project. And I had to put together some sort of temporary machine at the time. That was my advisor was develop his own machine for the QC use only, and there's a bunch of very powerful chip at the time that nobody else was using. So I got to put together and kind of my own baby here, and doing all this calculation on this tiny cluster throughout my PhD. And so that's something sometimes we have to do. And there are also softwares, right? So we also do a lot of calculation, and the QCD software itself has getting so complicated nowadays that we actually use quite a bit of community software, right? So this may not be that different from like LHC. You also have a lot of community software, right? And then we are trying to have some sort of format. So one of the money from the site there also providing the software development that we can have people whose job really focus on developing software. And we try to develop different steps of software so that everybody have their own favorite physics code. They can use multiple versions of some of the sub-label code so that everything can be reused as much as possible. And this can all be downloaded from the GitHub website or public. And then there are also multiple tutorials. So here's just one of the example of the summer school I organized at Seattle. So people having, this is one example. There are also multiple European schools as well that try to teach people how to use very different software, how to different type of problem on the laser QC and so on. And if you're interested, I think this is the YouTube lecture. Yes. Right. So after you have that, the next thing is to get a QCD vacuum. Like I said, the vacuum itself is not simple. In fact, it's very, very complicated on the latest QCD simulation. We spend way more, a lot more resources to generate those QCD vacuum. And if you have seen some of the latest QCD publication before, you see like very unusual for theorists to have so many co-author on the author list. A lot of reason is because of the gauge generation, right? So you had to collaborate with many people. Some people's job might be focus on how to generate the QCD vacuum as efficient as possible. And some people are thinking about once you have that, why do you use that for physics application, right? So that become really like very different way of how the theories work in general, right? So getting those, they are really, really expensive. They usually require the largest supercomputer resources to do the calculation. And because they are so expensive, actually, okay, oh, sorry, right. So take a step back, yes. So what we do is, because it's kind of keep changing, right? So we also want to do our calculation on top of that. So what we do is we sort of take a snapshot at a different sort of time, Euclidean time. So like, it's thinking about this, we are making movies, right? You have many, many friends of the pictures, and then you stack them together, right? And then you can really, if you have enough of friends, you can represent your original QCD vacuum as accurately as possible, right? And there in physics, you have to worry about other things as well, the correlation and various different things. But this does kind of simplify how we do the calculation. So people can save all this vacuum. It's very expensive. And then we can do the measurement on top of that afterwards. So you can think about physics application afterwards. So you have some time to think about that. And because of this process, we can also, people who done with the configuration, they can also share with other people. So now you can download a lot of very expensive QCD vacuum through internet as well, just like everything else. And so people try to form some kind of group. There's an international lattice grid, data group. So like people agree on specific data format. We don't want everybody to generate their own format, and you have to figure out how to translate their binary code to another one, right? So if you have a standard, so everybody doing the same thing, and then you can just kind of get that from internet. And we even have a couple of hubs, and one in US, one in Australia as well, at Adelaide. There's a big lattice group there, right? So then we can share those configurations a lot more efficiently, right? And they are, again, sometimes you are doing something that's kind of different from everybody else. You kind of, and there's no market out there. You sort of have to roll up your sleeves and do that yourself. And when I was doing my first postdoc, I was looking at something called exotic states. And there we really need the time duration to be much finer than the spatial one. And there isn't anybody have done that in the past. So we have to sort of do that ourselves. So that does happen as well. So once you have software, once you have vacuum, the next thing to think about is the fun part, which is the physics observable, right? So here, I say I take a snapshot of this QCD vacuum. Imagine this direction is all this XYZ space, and then this Euclidean time. And so when I do the calculation, I will be trying to create, say, I want to study the property of the protons. I will create the proton in one space-time. And I have correlated them and analyzed them in another space-time, right? And then, so that was just a proton by itself. So I need to put in an operator. It would be like some sort of meter to study its property. So I need to put, so my different kind of operators, like a different type of pole that will give me different information. And I can put it in various different space, and I can study the time dependence, and I can get some of those property out. And then after that is also, we try to output everything in terms of Euclidean time dependence. And there's a number of, we have to extract masses or matrix element that will give us the information that we want to study the properties. And this is where I sort of recruit a lot of undergrad in my group to kind of participate with the research experience. So this is one of my student, Kenza Hansen. She is going to be the third year now, and she was helping us with doing a number of analyses, and she was presenting this poster in one of the American Physics Society conference, special conference for the undergrad women in physics only. And so she was doing that. Let's skip ahead, right? And so, and the last thing is like, this is very similar to the experiment as well, right? You need to think about systematic. It's not the most fun part of a lot of research, but you also need to think about that, right? So how we need to kind of revisit a lot of parameters we put in the assumption at the beginning. We have different lattice spacing, so we need to think about that, right? And so we want to remove as much as possible so that we are getting the true physics, not the alligator sort of hiding behind the lattice and get us the wrong result. So there are various different things we need to think about, something called excited state, which we put in the operator on the computer, right? But it can have overlap with all possible radiating excited state. It all have the same quantum numbers, right? That we don't control. It's the QCD thing. It just does that, right? So we need to be careful. We have to very carefully analyze those. With some of the operator, we need to do additional realization on the lattice because we're regulating the space-time. And then we had to make sure that some of the assumptions we made, like the quantum masses, sometimes we represent that in terms of higher masses, right? There's a nice linear proportion. So we need to make sure the volume is large enough, the lattice band is small enough, and only when we consider all that, we can completely remove the systematic in the calculation and be able to take what we calculate and then compare with the real world. So people have been doing this for quite a bit. And so we start to kind of put together a number of calculations because sometimes we have phenomenology friends or experimental friends and saying, well, why is this latest good calculation different from the other ones, right? And so a lot of time is they are very different kind of systematic that's only relevant to us for doing the calculation. And a lot of people, you don't have to worry about that. So because, say for example, something is one of the systematic called chiral extrapolation, right? If you are closer to the physical power mass, your extrapolation will be more reliable. As you're far away, your extrapolation obviously is not going to be as good, right? So that's something we need to think about, but not something everybody else had to think about. So things like this can get a little bit confusing for people outside latest QCD. And so we try to put together some common systematic that we thought that could affecting the calculation. And we start doing some sort of rating system. A kindergartner can understand. If it's doing well, you get them a green star. If it's not so great, you give them a red square, and then something maybe they're trying to do something but not quite complete yet. They just do an open circle. So that's sort of help us kind of understand how the various different systematic that we all draw important in the community, right? And how much people have done the calculation. And then, then you can put the number together, right? If there are red star in the calculation, and there are some systematic that haven't been considered yet. So the error bar is actually bigger than what they listed in that particular paper. So they can kind of better to compare. Now you're more compared with apple and apple rather than apple and orange in a way, right? And so one of the things we do is to take something called tensor charges, which was actually forgot. It's an integration of the aqua, something called transvertive function, subtracting the down quark. So basically, this is like an area between aqua and down quark transversity function, between the two, right? And so by itself, it's just an area, a number. It doesn't tell you how it depends on something called Bilkin X, which is the fraction of the momentum, proton momentum to the matter protons, right? And from people are doing something called a global fit, where they try to combine various different experiments together. And this kind of transversity distribution require polarized target and sometimes polarized beam as well to get very, very clean experimental measurements. So it hasn't been very well studied yet. And so if you attempt to do that, do the installation, so you're going to get something very large error bar from the experimental data only. And this inner band here is when you have the latest constraint on the area, which doesn't tell you the shape, but it tells you what this area should be. And because it's much more precise, it's actually really impacting the extrapolation of the individual function pretty well, right? So by itself, we don't know about how this shape should behave, right? And then experimenters, various different experimental data tell you as a function of this X, but it doesn't constrain the function well enough. And by combination of what we calculate very well and what experimenters know, you can actually, together, you can make much better improvement on the unknown physics, right? So this is kind of the trend that we are trying to do. And another thing called fermentation function, which is not It's not something we can calculate directly on the lattice QCD. But you extract this sort of couple with some of this function when you try to extract the experimental data, and actually can improve that as well. So there's a nice complementary between what we do and we can work with people who are doing phenomenologies and experiments to kind of get the best out of some of these functions, right? And there are also things like we can take the form factors and we can look at the transverse plane and charge density, things like that. That's also something that we can do with the lattice QCD as well, right? So, I'm going to kind of focus on a few of the physics topics that we do really well, and there are a lot of things that's happening right now. So we're going to start with something called proton distribution functions, right? So I'll show in PDF, so which is everybody, different subfield have their own PDF, but this is our PDF. So basically, it's a property of how a proton could be a quark, anti-quark, gluons, could be a fraction of the way the Bilkin S comes in of the proton momentum, right? So they are also interesting properties of the nucleon. They are process independence, and they are actually allow the experiment actually contribute to that. The LHC also have quite a bit of information that can help us resolve some of the unknown PDFs. In US, there are multiple labs, Fermilab, Blue Heaven, and Jefferson Lab. They focus on different regions of the Bilkin S. Here's a picture from the Fermilab, which they have something called C-class experiment that would give us very unique access to the anti-quark distribution that most a lot of experiment can't. And there are some experiments at CERN, the campus, Amber for the meson structure. And there are some planning machine in US as well, something called electron-ion collider. And there's a similar version of that in China. And there might be a machine at HEC at CERN as well, all putting a very different forms of try to push into the region that we don't quite know in some of this property yet, right? And so there are many motivations. A few of them might be try to understand try to use that for prediction, right? So as we are searching for new physics, we want to have as much, we want to know as much about our standard model as well, so it can reduce that standard model error bar. So as we find a new physics, right, then you can have more confidence say about what we are, how much we know that's from standard model, or how much of that might be coming from standard model, new physics, if there's any. And they are also, like I say, also many processes also use the PDF by default, right? The IceQ also use quite a bit of PDF as well as inputs in many of their process. And they are also in the new physics form at HEC, the uncertainty in the PDF was also dominating theoretical error in his production cross-section. And here some of the plots still from other people. You can kind of see the model uncertainty, they were pretty big, and then compared with some of the cross-section in the PDF errors, right? And so on the lattice, traditionally we have doing something called moment, right? Which is we basically calculate the integrals of the proton distribution function. So there are a few common ones that we use in the leading ones. You have something called twist2 PDF. You have spin average on polarized, which is where you have the most of the data. And then you have the spin dependent longitudinal polarized PDF, and where that require a polarized target or polarized beam. And then you have this thing called transversely polarized, which is best measure or the polarized beam and target at the same time, but often you don't have that, so you have to have more complicated theory to compensate for that. And so that we have found from the most well-known to the very poorly experimentally known. And so we have been doing this since the 90s, when people started using lattice QCD calculation to study the structures. And so we haven't, in principle, if we can calculate enough moments, we can do an inverse transfer. So we can extract this S dependence on its own. And so that had been the goal for many, many years. But it is difficult in many ways because we do break the symmetry. So there's a price to pay. And so what happened is, as we go to the higher moment, we start to have what we call operator missing with a lower dimension. So you have something like 1/a squared. That become a problem because now we cannot take continuum limit anymore, right? And it become more problematic as you closer to continuum limit. So that's a big problem, right? There have been some idea to get around it, but as to try to push in that direction, but it's also more complicated as well, right? And so this is more beyond that. So when I was postdoc, it's literally the holy grail for a lot of people who try to do the calculation. And many people come before me failed. And I was like, I really want to think about how to overcome this problem. And my advisor at the time told me that, nah, don't waste your time. Too many people have tried before you. And it wasn't really able to get around. And so this applied to many, many things in addition to the pattern distribution function PDF I mentioned. It also applied to the other quantities such as generalized pattern distribution function, which provide what we call three-dimensional structure for the photons. They also you can also try to study transverse momentum distribution, a different type of three-dimensional structure as well, and many other distribution function that people cares about, right? And so up to about 2013, so basically it's sort of anything that requires Bjoch-Ness dependence has basically the own limit, right? And people who are doing phenomenology calculation, they make some assumption and they can do the calculation. So they are the only one able to provide any Bjoch-Ness dependence on any of those distribution functions. So until roughly 2013, Shandong-Ji, a person come up with a unique idea. And that's where we have really, really dry the lattice QC calculation. Anybody would like to see how much archive paper that's being published daily. You will see really a lot of lattice paper lately. It's all dominating on the structure side, dominated by this type of calculation. So there's a huge burst in the field of how many people are doing this, and they are applied to very, very broad different quantities of calculation, right? So the idea that Shandong-Ji come up with is like something called large momentum effective theory. And in short, it's sort of, so all the pattern distribution function was defined by Feynman in infinite momentum frames, right? So he was actually working on different problems. So this is kind of the side product that's come out at the time. So if you can somehow calculate large boosting momentum at the hadrons, and if they are large enough, then you can actually match that to Lycon in the field theory. And it's a really complicated, you can see more detail here. So you have to prove that the long distance infrared property had to be canceled out exactly, so you don't have that residual problems. And everything else can make up to the ultraviolet region, which you can calculate that due perturbation differences. So basically it's like, so what we calculate on the lattice, and then what we want to is kind of a different species, you have to put it out, but you can kind of match that with the perturbation. And because there is a perturbation calculation involved, that can be one loop, two loop, and so on, right? So this is very similar to how people extract pattern distribution function from experiment as well, except your purple block will be cross-sections, right? You'll have PDF, and you have various different coefficient on the other side as well. So it's a very similar property. And since then, there are other ideas as well, something called pseudo PDF. That's a very similar idea, but it goes to the Lycon to a short distance rather than momentum, right? And then there are various other ideas that have been coming out from various different lattice groups. Some of them revisit their old idea. They become really doable today in today's computer software. And so they have been a lot of bursts of different type of calculation that are coming up, right? So here just a short plot. This is roughly from 2013 to about today. And so they're having like all these methods sort of popping out. And that's very, very unusual. Like I said, we have been doing 20 years of the moment calculation. It's just one method, right? Nothing else. Now we have many different type of method. And this is just the first calculation of the method, right? There's not enough space to put everything there, right? So they would just highlight out the first method that you can continue to develop pick one on the method, and you can do really wide variety of calculation, right? And then there are also a lot of first physical quantity that we couldn't reach before. Now we have very different, again, this is only point out the very first calculation that we have first physical parameters calculation on the nucleons, and they are very different mesons and other structure that we can look at was completely impossible 10 years ago, right? So, so in short, if you just look at the leading twist to PDF, right? They have this unpolarized, nuclear polarized, and transformative polarized, right? So this is the summary taken about roughly 4 years ago. So people have been doing this for a few years, and they try to do all the calculation at the physical power mass or extrapolate to the physical power mass from this red point here. And because we introduce another parameter, which is the momentum dependence. So we want the large momentum U to be as large as possible. Similarly with what we want lattice spacing to be as small as possible, right? So this has become another dependence that we kind of have to keep track in terms of how big the systematics are. So most people just kind of reporting the statistical error is more the traditional way of doing the calculation, right? And so this here are the latest calculation on its own at the time. And then you compare with the global fit, which is the last 3 color over here, right? So in terms of unpolarized distribution that we don't have, we actually just started doing this about 5-6 years at a time, right? Compared with 60 years of unpolarized scattering data, latest calculation hasn't quite beaten that yet. But if you start to look at the polarized trend, you start to turn on the polarization, right? So you see the latest actually can be more comparable. Here you actually need to make some assumptions because polarized data is not easy to analyze. And so you go on to the transformers polarized, you can see the latest actually much more precise compared with that. And so there are some sweet regions of that we can immediately impact. And then with the polarized PDF, we will need to look up, continue improve our calculation and so on. Right. So there are quite a bit of developed over there. Right. So one of the things my group is looking at is try to think about the unpolarized PDF, but in the strange sector, because that's where you don't really got very good experimental measurements. And so here is one of the summary that's made by a group called CTEC Genetic Collaborations. And so what they were comparing at the time is the different color corresponding to different global fit. And what people find is sort of like there are some regions they kind of, but they seem to be agree with each other. And then we go beyond the region that you have data, and everybody predict very different large X behavior for this particular PDF. And furthermore, is a lot of people had to make assumption to get non-stable PDF for the strange quark. And so one of the common assumptions is just assume the strange quark equal to anti-strange quark because they are all very small, but there's no reason to do that at all. And then sometimes you kind of tie them with anti-Abend quark by linear assumption. Again, it's just so because none of these are physics-based assumption, but because the data is so hard to extract, you can make many assumptions. They all fit the data reasonably well. And so that's why you have different assumptions that literally lead to very different extrapolation outside the region you have data, right? So we are thinking about how we do this on the lattice, right? So what we need to do is now our pole is somehow what people call disconnected. You still have a lot of complicated loop in the C that's kind of interacted with that, but the quark itself doesn't connect with the valence quark, right? So we need to calculate this type of diagram, which is a little bit more complicated than usual. But so what we do is we look at the matrix element. So our matrix element is actually real power of matrix elements corresponding to the differences of the strange minus anti-strange, which is perfect. We can check that assumption. And so unfortunately, what we see is like, if people are actually doing something right, we get all our data points is like around 0 right there. And there's only one group at a time that didn't make an assumption and then PDF. And so their result, their uncertainty is pretty large, which is this grid band over here. And so we started to think about how do we make predictions. So we work with CTEC group, which made that assumption, strange equal to anti-strange. So if they relax that condition, they get something much larger error band, which is this blue error band here. And so we take the latest real part calculation, which give us the strange minus anti-strange, and we try to be a little bit more conservative, say, we instead of taking the trust everything we have, because our PDF, the region we can trust the latest PDF, also momentum dependent here. So let's say we try to be conservative, we pick 0.3 to 0.8. And then we see immediate impact for this gray slash regions. So it improves some of these regions of the uncertainty, and in some region now as well. And we started asking, well, so there's a point to continue improving this latest calculation. Is this the best one can do? Or if we need more computer time and we can get better result? And it turns out, yes. So if they try to reduce our error by a factor of 2, and there's a significant impact in this green backslash regions, right? There's a huge impact from the blue to the green by reduce our error by another factor of 2. And furthermore is they were able to make this prediction improvement continue to this very small S region that we can currently trust our latest result from, right? So this is all their prediction. And that's where a lot of machine, like the future EIC and virtual EC is going to be very good impact in the small S area. So this is another example of like putting lattice and the global fit together, that we can actually make really good prediction in the region that we individually cannot get to, right? And there are also things like Gluons, so I'm taking out more time than I like. I'm going to move ahead. So there are also things like phenomenology. So that I mentioned is 3-dimensional structures. So it's like thinking about, I'm trying to make a most visual thing possible. Maybe do the, what's the movie again? I forgot.
That's one of the Ant-Man.
Yeah, Ant-Man, that's right. There's a for the very first time. And so that's something, a lot of improvements. So they are also challenged in this method. They're having a lot of work that have been done, but they also a lot of challenge. We haven't really reached very, very large momentum yet. So the largest momentum that people use right now is 2 or 3 GeV, right? So that's still really close to the nuclear mass. So we like to get beyond that. And there are a lot of things that one had to worry about. The noise, signal to noise will become a problem because this kind of non-local operator is not something laser QC are very good at. That's why we have been doing moment for 2-3 decades, because that's something, method is great. So they are very different things one need to think about. And if you are interested in thinking about those problems, there's a nice white paper for the one of the snow mass, high energy in high energy community planning in the US, we had write a short paper for that, right? And there are also things that we want to think about. I say, right, this is something like the PDF is on the right-hand side. So, how do we extract them with the last model dependence? So one of my undergrad was looking at the machine learning to try to pull the structure from that as well. So there are many things that can interplay with different area. And there are also a lot of people that's doing some of these topics I didn't have time to talk about, but notice there are some local interests here, right? So there are like, there are people studying a lot of property of the nucleon that can be kind of connected with some of the ongoing search. For example, the nucleon form factor or transition form factor, that could be inputs for the neutrino experiments, experiment like Doom and so on. There are traditional coupling that could sensitive to the non-vector minus axial interaction. that can help us probing some of the possible scale of the particle in the multi-TeV regions. And say if they are dimetal or electric dipole moment detection, and there will be some coupling coming from the nucleon that's not quite easily obtained elsewhere, the latest people are taking these questions. So they are really integrate. So in short, so it's a very exciting area to use lattice QCD to study very stable structure, pion nuclei, and so on. We have a lot of traditional method. We have been able to get down to control that systematic and get something really precise to remove all that error, the potential alligator in the lattice. We had this new idea, a very, very simple new idea to try to get the calculation of Bilkin dependence. So they are really driving a lot of calculation out there. There are some popular Lamel and pseudo-PDF, but there are also other different methods people are investigating. They have a little bit of sort of limitation in terms of precision and some of the limitation on the momentum. We want to get as large as possible, but there are also some opportunity for all the young people out there as well. And so to conclude, we are hoping to get more and more experimental, not just taking the experimental cross-section, but we'll also be able to use what we calculate on the lattice, especially the Bilkin S dependence, and together we can make better discovery from very different structure. So that's all my talk. Thank you.
Thank you very much.
Maybe can I ask something? You mentioned there the strange quark PDFs there with assumptions. Will there also be new data which for thank you.
Yes.
That slide.
I think there was some experiment a while ago, a long time ago, that using ions that were able to give some of this information, but they are really noisy and people haven't been able to do more calculation. I know there is some measurement coming from LHC, probably another few years that can help. I think if I remember correctly, probably the X or anti-S separately, not the combination of that. Yeah, but there will be some data from some of this LHC round in the upcoming rounds, and some of the experiments are coming out in another few years.
Yeah, thanks.
I mean, just since you're showing the slide, just to follow it up, I mean, you sort of implied that the result is somehow unexciting because it's at zero, but this would allow you to say, to put some sort of lattice-inspired bound on the deviation from the assumption.
That's right.
That they're both the same. And I would have had no opinion whatsoever on what. Presumably there is some deviation, right? But I would have had no opinion on what the size of the likely deviation was.
Right.
I couldn't have told you.
Right.
I don't know how you would even answer that question, but this would seem to give you such a bound, yes?
Right. So what we do is you kind of take this coordinate, what we call this coordinate dependence, and to the momentum dependence, and then you have to do this something called matching, which give you the Bilkin S dependence, which is still mostly consistent with the zero, right? But now you are constrained in terms of the Bilkin S. Sorry, this is X. Unfortunately, got cut out here, right? So we actually change that to the momentum space. And so this gives you the upper bounds of that symmetry. And as you put this into the whole global fitting frameworks, and you try to keep that the strange and anti-strange to be within that region. And you can actually, so I don't have the plot for the strange by itself, but then you can sort of relax that and look at the strange and anti-strange themselves as well.
And does that constrain global fits? Does this constrain global fits in any meaningful way?
We'll compare without the constraint, yes. And just it currently is not as significant, but in the future, when we continue to reduce this error, that can be more significant.
I I have a few extremely naive questions. Maybe I'll do the slightly less naive one. So the lattice results seem to come up quite frequently in the discussions around the anomalous magnetic moment of the muon, where the lattice results seem to be suggesting there is no tension there. Can you just give a sort of expert's comments on these results? Like, if a lattice group makes a prediction and it lines up with the experiment, is that the final word in your opinion? Or
so yes, this is probably where we color recoding. But so that goes to that. Where's my tape? Okay, the table in terms of you have to be carefully looking at the various different systematics. So yeah, this one, right? So you could have, so the muon geometry is one of those examples. You see the lattice group, among lattice group who calculate some quantity, they vary a little bit, right? And that's where you need to count down all the systematic that go into, that's sensitive to that particular process, right? So the muon geometry itself also have they are various different contribution. They have the glue have to demonstrate they have that under control. And sometimes certain approximation work well with, one of the things I didn't talk about is that we actually have different fermion engaged action than the continuum, because now we have additional lattice spacing breaking, right? Sometimes you want to, some people try to preserve the chiral symmetry, so they can do that by putting back certain term in proportion to A or A squared. And you go to continuum limit, you go to the same Dirac equation, but on the lattice they are vary. And that can bring in the systematic that can play a different role in one glue's calculation and another, because they use different setup, right? So this is where, like, you know, somebody who are expert in these fields, and they can make similar table, and they can put in all the important components that need to be considered. I know there is this like a role poll that people are talking about, and some people try to overcome that by using a lot more. Those snapshots you're seeing, they had to explain that a lot more to see how big that constraint is, and they had to increase the volume way bigger than fitting that hadron by itself, because the calculation itself is so precise. And so those are, they can play a factor in those calculations, right? And so they should be something like this, but probably have a different component that's sensitive to those calculations. And then when people, hopefully somebody will do such a table soon, so that we can see how you can compare from one good calculation to another, right? Yeah.
Can I ask, you talked about the pions and nucleons, but can you tell us a little bit about the eta prime calculations?
Oh. Okay, so eta prime, so a lot of time you see we do calculation that's unstable hadron on QCD, right? So pion and nucleon is one of them. Eta prime actually decay within QCD. So first you had to get that spectroscopy very precisely determined. And then when the particle decay, there are people who were thinking about, so on the lattice, the decay become more complicated. This is where we pay an additional price as well, because you can have the hadron doesn't exist in a continuum that can become a stable state on the lattice QCD, on the lattice. And so you had to have consider a bit more final state than the continuum. And there are a number of groups that's thinking about that, to have very multi-hadron, 2-hadron final state, 3-hadron final state. And so we had to first sort out those theory first before we can do those kind of unstable particle structures. Yeah. So it's progress ongoing, but it's actually not, it's a little bit complicated, yeah, to do so.
So when you talk about comparing and combining the results of different collaborations, so to what extent is it, are these measurements of a certain quantity independent, if in light of this sort of sharing of code and sharing of algorithms and things like this?
So I think they are sharing codes, and yeah, there are some vacuum that have been shared. And so when you combine, I don't think I took a slide for that. Right. So if we are not combining different lattice calculation together yet. There should be somebody doing so, but people I don't know whether this happens in experiments as well. Just so people have different way of quantifying their systematic, and you don't want to overly conservative quality error bar to be them implying minimal impact. You can be too aggressively making your error systematic too small. You seem to have very strong say about certain physics, but you might be too aggressively, discarding something else, right? And so people couldn't quite agree on what would be the best way to code that. So there is not a way to combine, at least among the community. So when I do a combine analyze myself for the tensor charges GT, they happen to be using different vacuum, and so I can take them as individual vacuum would be like individual examples, so they are uncorrelated. So I can put them together easily, and I just put in all this additional lattice artifact in the fitting parameter, and we combine them together. Yeah, but more universally, yes, that would be a good idea, but community couldn't quite get it together and do that. Yeah.
Any final questions? I think we can thank Huey-Wen Lin again. Thank you. That's right.